Hello. Um, so in this video, I want to continue with our efforts to learn about forces and kind of practice solving problems with them. So I want to go through a few simple problems and kind of work out how to just go through the analysis or an analysis with forces. So some of these examples are clearly inspired by our homework questions. So I won't solve them all the way to completion, maybe, but I will give the basic idea, or I'll change the numbers. Okay, so the first, let's just kind of review what are the basic steps to analyzing a situation with forces. The first thing you would need to do is is to identify all the forces. Step two, construct a free body diagram. So that would mean you draw all the forces emanating from the object as they really are in real life. In particular, that means pay attention to angles. 3, break forces into components. Okay, so you want to break the forces into components, the forces in the free body diagram. Oh, I want to say, in the free body diagram, you only include forces. You don't include acceleration or anything else. All right, break all the forces into components. And then step 4, we want to add up all the forces. Now, the way I will do that is to construct a force table. Now, you don't really have to use the force table idea. You can just add them up in components if you understand what you're doing. But this is just a kind of a device to help us organize our work. And then 5, work out F net in each direction. X equals MAX, and F net Y equals MAY. Okay, so that is the basic strategy for solving a problem involving forces. And you would do this for each object that's relevant. So each object that's relevant in the problem would get its own free body diagram and go from there. Okay. Let's do a simple example here. So one of the sapling questions is like this. There's a ceiling, there's a ring, there's a rope which goes down like that, and then there's a hanging mass like such. And we're going to assume that there's no friction at the ring, which means that the ropes are going to be at equal angles. Sorry, I'm looking at the. Okay, so if there's no friction, what that actually means is that the angle here is the same so equal angles. And also it means that if I were to label these T1 and T2 for the retention on these two ropes, it would also say that the magnitudes of tension 1 is equal to the magnitude for tension 2. They just differ in one kind of goes to the right and one goes to the left, but they have the same size force. Okay. So what we can do, what I'm going to imagine is, let's assume that, um, let's assume that this is a 10 kilogram mass and it's hanging, and we'll assume the wires are massless and the ropes are massless and the ring is massless. Um, and let's assume that theta is 20 degrees. Okay. So let's go through the process and try to figure out what tension needs to be on each of the vertical ropes. So we ID all the forces. Well, first of all, we have to choose an object. So in this case, what I'm actually going to do is make the ring my object, and then the forces acting on it are going to be the two tensions, which have equal magnitudes. And we have another tension on this rope, but because it's not moving, we know that the tension coming from this rope has to equal the weight of this 10 kilogram mass. So I numerically know that that's the case. So what I'm going to do is I'm going to call this T3, but it equals numerically mg, which would be 98.1 newtons. Okay, so just the third tension here numerically has a size equal to the weight of the falling mass. Okay. All right, so let's go. So we've got the forces acting on the ring. So we study the ring, and the forces are tension 1, tension 2, and tension 3. The ring has no significant mass, so don't worry about that. I draw my free body diagram. Then my force tension 3. And now I can't remember how I labeled it. There you go. Tension 1, tension 2. And we're trying to find, so we want the magnitude of tension 1, which equals tension 2. They're the same in magnitude. All right, so there's my free body diagram. And I've got this angle here. So let's just write that. That's 20 degrees. Very good. All right, now, this is what I'm trying to find. The other thing I know is that this isn't moving. It's stationary. It's in equilibrium. Which means F net equals 0 in both x and y direction. So that's just an aside. That's something else I know about this problem. To proceed, what I want to do is break tension 2, and I want to break it into components. So I would have T2y and T2x. And this angle would be theta, 20 degrees. So now if you look at this triangle, it's a little bit unusual for us because normally the x direction is associated with cosine and the y direction is associated with sine. But when I look at the way this triangle is drawn and the way the information was presented to me, I see that um, the x direction is opposite the angle. So what I have here is that T2x divided by the magnitude of T2, the hypotenuse, is going to be sine theta, which should be 20 degrees. So therefore T2x equals T2 sine theta. And similarly, I work out that T2y equals T2 cosine theta. All right, so that's how I analyze the components of T2. For T1, I'd really just do the same thing. So I'll write that down in a minute here. So I've got free body diagram components, and I need to make my force table. All right, so for rope number one, it's really the same analysis. The magnitudes are the same, all that's the same. The only thing that differs is that it points to the left, so the x component will be negative. So I will say that T1x is going to equal negative T1 sine theta, and T1y is going to equal T1 cosine theta. And this is positive because tension 1 points upwards. All right, so now let's construct my force table. So in the force table, I put the forces. I write the x components, and I write the y components. So I have T acting on the ring, I have tension 1, which in the x direction gives me minus T1 sine 20. And the y direction I get, that's fine. And I get T1 cosine 20. Then I have tension 2. And tension 2 points in the positive x direction, and the magnitude of tension 2 equals tension 1. So I'm going to use that. And then I have tension 3. And tension 3 has nothing in the x direction because gravity pulls it straight down, and it's equal to minus mg because it's going to pull downwards on the ring. Okay, so these are my forces, and I can add them up to find the net force. Now these just add up to 0 because they equal and opposite things. And these, they will equal 0, but we can turn that around and solve for T1. So look, this and this, these two terms are the same. So I get 2 times T, the magnitude of T1 cosine 20 minus mg. All right, so that's my formula for the net force. And I go back to my problem. Because I know it's an equilibrium and the net force is 0, it means that 0 equals 2T1 cosine 20. Oh, I lost my absolute value sign. Minus mg, or the magnitude of T1 is mg divided by 2 cosine of 20. And we can type that into our calculator. And if I'm doing that right, I'm getting 52.2 newtons. Which kind of makes sense because the weight was almost 100 newtons, 98.1. And we're splitting it equally between two pieces. So you'd expect it to be, something like 50. And then it's not exactly 50 because these are off at an angle, which means the actual tension on the rope is going to be more. So it's kind of like if you imagine trying to lift something off the ground, you don't do it with a rope with really shallow angle, you just want to pull it straight up to make it as easy as possible. Well, all that amounts to saying is, in this case, in order to support this weight at an angle, you need something a little bit more than half the weight. So 52.2 seems like a reasonable result. All right, so that's how I handled that. What are some key strategies or tricks that are, I don't know, ideas? I labeled my diagram of what happened, and then I drew my free body diagram, and I didn't know everything. I didn't know all of the quantities. In particular, I didn't know what to write down for T2. That's okay. I just wrote in the magnitude of T2, just symbolically. And that actually becomes a positive. The fact that I didn't know it becomes a positive because ultimately you turn it around and that's how you deduce the appropriate value. So what happens frequently is when people get to a problem and they don't have a number that they need to plug in, they freeze. Instead, just come up with a symbol, a new variable for that thing that you don't know, and just write the equation down. After you do that, then you use that symbol to deduce the thing you're missing. Okay, let's try another problem. So another problem we have on sapling is there is a tetherball sort of situation where you have a ball on a rope, and we are told that there's wind. So there's wind acting to the right on this rope, which has some tension T. I don't know what T is. In fact, the goal of this problem is to find the tension and the angle it makes with respect to the vertical. So we want the tension and the angle. Okay, those are the things we want. What we know is the mass of the ball is 1.55 kilograms. We also know that the rope is taken to be massless. That's easy. And let's say we're given that the wind, the force from the wind is, let's just say 10 newtons. Everyone's numbers are going to be different. To the right. Okay. All right. So I have lots of information, and this is the force of the wind on the ball. So I have lots of information about forces acting on the ball. So let's focus on the ball. All right. So that's our plan. Our steps are to identify the forces acting on the ball. So the forces would be, well, there's gravity, there's a tension, and there's wind acting on the ball. And so I can draw my free body diagram. I have the tension, which acts at some angle. They ask for this angle, but using opposite interior angles, it's the same as this. There's a tension. There's a weight, which equals minus mg. And then there's a wind force pointing to the right. So there's a free body diagram. The wind force and weight are kind of nicely aligned with coordinate axes. So we'll just work with X and Y, the kind of as vertical and horizontal. And the only thing I have to worry about in terms of trigonometry is the tension. So what I can do is break the tension force into a horizontal component and a vertical component. This will be Tx, and this will be Ty. And notice Ty is going up because it's positive, and Tx should be to the left, should be negative because the rope pulls the ball back to the left. And I see that Tx is opposite theta. So I can say Tx, I don't know what it is, but I can just write down a symbolic formula for it. T sine theta, and I put it a minus sign because it was to the left. Ty is T cosine theta. All right. And so I've drawn my free body diagram. So I identified the forces, drew my free body diagram, wrote things in components, and now I want to construct a formula for the net force, and I'm going to use a force table. Identify the forces, and then X and Y. Okay, so let's do the easy one here. I have gravity. And that is 0 in the X direction, and it's equal to minus mg in the Y direction. And then I have wind. That is only in the X direction, so that's going to be 10 newtons, 0. Let me just double check I have the right number. Yes, 10 newtons to the right, so it's positive 10. And then we have the tension on the rope, and that's going to be minus T sine theta. And then the Y direction is going to be T cosine theta. Add those up, and I find, well, okay. So now, in the situation, the ball, maybe I should have said this. Again, this is a equilibrium. So basically the angle adjusts so that the tension angle adjusts so that the ball just hangs there just stationarily. So that means the net force will be 0. All right. So what we're going to do is find a formula for the net force, which says, so in the X direction, I get 10 minus T sine theta. In the Y direction, I get T cosine theta minus mg. And these all must equal 0 because it's in equilibrium. All right. If these equal 0, so I can just write that out again. 0 equals 10 minus T sine theta, or you can turn that around and say T equals 10, sorry, T sine theta equals 10. And similarly, I can say T cosine theta equals mg. All right, sorry about that. I had to deal with kids in the other room. All right, so now this is a little bit tricky to solve. T sine theta is 10, T cosine theta is mg. How can you do that? it's not a linear equation. It's got trig stuff. There's a trick. Let's call this equation heart. Let's call this equation square. Take equation heart, divide it by equation square. So that means divide the left-hand sides and set it equal to the ratio of the right-hand sides. And if you do that, the tension divides out. So that would give us t sine theta divided by t cosine theta would equal the ratio of 10 divided by mg. And the t's cancel. Sine over cosine is tangent. And so we'd say tan theta is 10 over mg. And plugging in my numbers here, remember the mass was 1.55. So this will give me, plugging it all in, taking the inverse tangent, I get theta is, I'm getting 33.3 degrees. All right, now what do we do from here? Well, once we get to here, we go back and then substitute into one of these equations. And I'll use the one with 10 because it's a nice round number. And I know that t sine 33.3 equals 10 newtons. Therefore, t is going to be 10 divided by 33.3 or sine of 33.3. And typing all that in, I get 18.2 newtons. All right, so those are two problems that people sometimes struggle with. Hopefully that's enough to get you started on these free body diagram problems. All right, I'll let you go.